This example is also considered as a van der Monde type identity. It follows the idea of a van der Monde identity, but it's not necessarily equivalent to that, but it's almost similar. That's why it's called a van der Monde type identity. Let's show that the product of n combination M and M combination R will yield into this result here. We have n combination R times n minus R combination M minus R. So we're going to show that this is true. Now, in the previous 4 videos, we just manipulate one side. Here, we might need to manipulate both in finding ways that they are actually equal to one another. So, how do we illustrate that? Let's not forget that if we have here n combination R, it's just equal to this form, its formula, n factorial over R factorial times n minus R factorial. So we're going to consider that here because both sides are products of combination expressions. It's just that they have different representations. So just simply attack it in that way. Let's start by the left-hand side. I would like to start with the left-hand side to see what is its simpler form. So for our n combination M, so yeah, this is now the start of the proof, if you may. So for your n combination M, that's n factorial over, instead of R, you will have M factorial, then n minus M factorial, times the result of M combination R, you have M factorial over, you'll have here, instead, you will have here R factorial, that's your number of elements to be taken from the set of M elements, and minus times the M minus R factorial. Okay, now from here, I supposedly our goal is to manipulate one side to arrive the other side, but here we might see something to be simplified. As mentioned, we have here M factorial in that, and of course we are talking about the product, which will lead to a similar result. Okay, so in the meantime, let's just stick to that, and we'll return to that later. Take note of that. Okay, we will arrive into that portion. Now, how about n combination R times n minus R combination M minus R? So following the idea, for n combination R, you will just have this n combination, n factorial over R factorial times n minus R factorial times, now this is where it gets complicated. Take note, this is now your n and this is now your R. So notice what happens here as well for our second term on our denominator. So you will have here the n minus R factorial over, so you have m minus R factorial, which corresponds to this, but our next term will be the difference of the two, n minus R minus m minus R factorial. Okay, so take note of that, and then let's move forward here. So n factorial, again we are stopping here in the meantime, we will return to that, over R factorial times n minus R factorial times n minus R factorial over m minus R factorial. Then by removing the grouping symbol, you will have n minus R minus m, then plus R because of a double negative property factorial. Now, continuing that here at the bottom, n factorial all over R factorial times n minus R factorial times n minus R factorial over m minus R factorial. Then the result of that, since you have here minus R plus R, that's 0, what remains would be n minus m factorial. Now, looking into this form, without canceling this first, because we also have a common there, look into the relationship of that, and let me copy this one here. The first, or the left, the left-hand side. Okay, this is the left-hand side. Oh, I think it would not be clear because it's white, so let me write it here. This was our n combination M times M combination R. If you may, I'm gonna write it here for your guidance. N factorial R factorial n minus R factorial times m factorial over, yeah, r factorial times m, sorry, this was actually m, then m minus r factorial. Take note that this blue one here is the result of this. So you have n combination r times n minus r combination m minus r. We're trying to show that these two are just equal. But when you look into this form, even if you're going to multiply numerators and then for your denominators here as well, you would see them differently because the numerator of the blue one is n factorial, sorry, the blue one. For the blue one, the numerator for that is n factorial times n minus r. But for the red one, that's n factorial times m factorial. Generally, they are not the same, right? Because you have here n minus r and m. So how can we show that these two sides are equivalent? Now, this is where we're going to return to the cancellation. Supposedly, if you're proving identity, just need to simplify one side and make sure that it returns to the other side, or vice versa. Now here, we will be introducing the cancellation, which is still mathematically sound, because you will have here n minus r factorial, n minus r factorial for the blue, and for the red one, you will have here m factorial and m factorial for that. Because if you're going to multiply that, let's talk about the blue. So for the blue here, this is again n combination r times n minus, sorry, that's minus, combination m minus r will result to n factorial alone because this is already simplified over, you have your r factorial m minus r factorial times n minus m factorial. I'm sorry, I made a big mistake. This is actually m. Okay, red one. Yeah, n minus m. My bad. That's why I was thinking it would not be it would not simplify properly. Sorry for that. And our red one, here comes the red one. N a combination m and m combination r is again n factorial as that was removed over, you have n minus m factorial times r factorial times m minus r factorial. Though disarranged, the denominators would yield to the same result. As you can see, again, my bad earlier, this was m. As you can see, you will have the same result. So this further clarifies that n, let me use now a general color, n factorial over r factorial, m minus r factorial, n minus m factorial is just equal to the n factorial here, n minus m factorial, r factorial, m minus r factorial, which both of them, for this one is this is actually n combination r, then n minus r combination m minus r equal to n combination m times m combination r. So I don't have much space. Let me place here hence, and let's me close this one. Even if the identity starts with that, using symmetric property, they are just the same. So again, I made some corrections a while ago. Please bear with me. I'm also trying to look into the appropriate steps. I made mistakes, but I have already clarified that. This shows that this van der Monde type identity is true with this. Now you can try values for n, m, and r as long as they are all greater than 1, and you could see a result that might be similar, but this is in general form. Thank you very much for watching.